Even and odd functions are a topic in algebra, mostly how to identify them, not really so much what to do with them or how they're used. But even and odd functions, they show a sort of symmetry. So first I'm going to say even functions. What we do is we will put negative x into the argument of the function. So if we have f of x and we put in negative x, that's going to be f of negative x, and this function is even if this is equal to f of x for all values of x. So this is typically like x squared, even powers of x. There's other functions that I haven't really covered yet. Maybe in other videos I'll explain if they're even or odd functions. But we plug in f of negative x, and if it's the same, then we get a even function, usually even powers. So let's say, like x squared. We plug in x squared, and we want to know even or odd. Well, we do negative x, and then we square that, and that happens to just be x squared, which is the original function value. And what this means is that when you go to graph this x, y, when you go to graph this, you can graph just one side of the graph. Like for x squared, it's a parabola, so it's going to look like that. It's going to be symmetric about this y-axis. I guess the y could be right there instead. And when it's symmetric about the y-axis, is you just copy what's on the other side and just keep going. Imagine that's perfectly drawn. So that's basically the pattern, is that it just kind of repeats itself on the other side of the y-axis. For odd symmetry, it's a little bit different. We're still plugging in f of negative x into our equation, or our function, the argument of the function. But instead this time, now we want it to be negative f of x. So what this would mean is that, like, it's, the negative of the function value. So for instance, x cubed would be an odd function, because when we take a negative value and cube that, we are left with negative x cubed, which does not say positive. So when you go to graph this, now instead of just being symmetric about the y-axis, it's symmetric about the point, the origin point, the 0, 0. And we can kind of go the same pattern. It would almost follow like a parabola, but instead of being symmetric about that, now it goes in the opposite direction. Sometimes functions are neither odd nor even, so there's like no symmetry between them. And this happens when it's not f of x, nor is it negative f of x. For instance, if we have f of x is equal to, say, x to the 4th minus or plus x cubed minus 2x plus 2, plugging in f of negative x, negative x to the 4th plus negative x cubed minus 2 times negative x plus 2. That would give us x to the 4th minus x cubed plus 2x plus 2, which isn't negative f of x, and it's not f of x. It's almost, but not quite neither of them. So it holds no symmetric value. The importance of these lies in calculus when we're trying to find the area under a curve, for instance. Let's say we're trying to find the area under x squared, you know, this area under here. We can make arguments based on symmetry. Because we know this is an even function, we could just take, say, from here to here instead of going from here to here. It just makes things a little bit easier in terms of finding out how much space is underneath this curve. So it kind of says you could just double it. Now when you get to odd functions, we want to find the area under the curve. Again, you know, this area under here. And when we're below the graph, it's kind of the area above the curve. So let's say, you know, these 2 points are evenly spaced. Let's say this is x is equal to 1, and this is x is equal to -1. And we want to find out how much area is underneath it. Well, due to symmetry, we can say that these areas cancel out and it just becomes 0. So this is the basic idea for even and odd symmetry. And thank you for watching. Oh, that doesn't look like a 1. Okay, now it does. Thanks for watching.